Voila. Okay. All right. So we're going to start with the most beautiful definition in mathematics, and that's of the zeta function. So the zeta function is defined as follows. So this is a function which is the sum of 1 over n to the s, and it's been a source of great amount of inspiration over many centuries. So, and the reason perhaps of the greatest current interest in this function is because of the remarkable discovery of Euler that this is a product over all primes.
So for now, you look at it as a function on the complex plane, right?
Yeah, so we'll get to that. Product of all primes, primes P. Thank you. Yes, please feel free to interrupt anytime. So I should say what I say always in my lectures when I teach. I have a plan for the lecture. So my goal is to, get through my plan. But your goal should be to, do your best so that I don't reach the end. And it's in the tension between these two goals that learning will happen. So yes, I will get to in a minute of what S is. So when Euler was considering this function, it was for real numbers, and Euler, was not. I guess he didn't care so much about keeping track of convergence. But if we want this to converge and the expressions to be meaningful, then we should consider real numbers bigger than 1, because otherwise the expression will be divergent. But the real key insight of Riemann was that we should consider this as a function of complex variables. So real part of S bigger than 1. And one can easily check that this expression converges for real part of S bigger than 1, and that it diverges for 1 or smaller. Now, the left-hand side, so 1 over n to the s is something that you can, give anybody who learns some fractions and maybe some powers. So possibly even elementary school kids, you can give them the definition of zeta function. So that's one of the reasons that I like this definition. On the other hand, the right-hand side is a bit more subtle. Of course, one needs to know the prime, but why they are also related. So this is the restatement of the fundamental theorem of arithmetic, which was known to the ancient Greeks. Presumably the Pythagoreans knew about this, because that's how they would have discovered that root 2 is not a rational number. But of course, this form, to connect these two dots, required the genius of Euler somehow to be able to rewrite it like this. But real decisive step was taken by Riemann for considering complex variables. And so let me write down Riemann's sort of viewpoint as this. So let me write down the Riemann, so what I call the Riemann hypothesis package. So the Riemann hypothesis package goes like this. So first of all, the crucial observation of Riemann was that zeta can be continued to a meromorphic function on on C with only one singularity, with only one pole, one simple pole, simple at S equals to 1. So this was a crucial observation, and it's sort of, so we'll talk a lot more about the Riemann zeta function and its and what Riemann did next time, but it was sort of a revolutionary insight, because it's the way I like to think about it is like, imagine you had a book, like a scripture, the Bible, and you only knew like the this last half of the book, which was less interesting, say. And what this says is that you can sort of rediscover the whole book from that last half. You can sort of reconstruct the whole thing if you're clever enough. Okay, so and there's a canonical text somehow. So this was Riemann's crucial discovery, but he went much further. So so in other words, a function that's a priori defined only for real part of S bigger than 1 is in fact defined for all complex numbers with a singularity at S equals to 1. And second, Riemann discovered a functional equation for this function. So, and for that, it's better to actually consider something that's called the completed zeta function. So let my zetas are, so let zeta hat be the completed zeta function. So in Riemann's notation, this was the Riemann z function. So this is, by definition, is the zeta function times some fudge factor involving what are known as gamma functions. And we'll talk more about these next time. And once you complete it, then the functional equation can be conveniently written as zeta tilde of S equals zeta theta of 1 minus S. Okay, so in other words, the zeta function has a symmetry along the line of real part. So if you consider the complex plane, which looks like this, so this is the 1, which is where the singularity is. So let me denote it like that. And then we have here 1/2. And this is the critical line, so to speak. And there's a symmetry. Riemann says that there is a symmetry, this function on this side and on this side. And this fudge factor is a bit mysterious, so I will talk next time. I mean, we can write down the formula for it, but how to actually understand it and why does it appear is a bit mysterious. And in fact, there's a school of thought that the reason we cannot prove Riemann hypothesis is that we don't really understand the geometry behind this fudge factor. But I will discuss that more later. And somehow this functional equation in some form was also discovered by Euler, apparently. So I'm sort of looking into the history, and but I'm not exactly sure how. So I have to read the historical article more. But apparently some version of it was also known to Euler. Though, of course, Euler was not nearly as careful as Riemann in terms of issues of convergence, etc. There's a comment in the chat.
Yeah, I wanted to ask about the simple pole. It is not symmetric, right? There's no pole on the other side.
Yes, so you're right. So when I say symmetric, I really mean once you include that fudge factor. So I shouldn't have drawn this pole. Once you include that fudge factor, then this pole also goes away. So then really it becomes symmetric.
I see.
Thank you. Other questions? I should emphasize that this is lecture by a non-expert. So anything that could be wrong, that may be wrong, could be wrong. So please, yes, stop to ask about.
Hey, Masood, I have a question.
Yes, Bailey.
This zeta hat, is this the analytic continuation, or is this a new function that you've created?
This is a new function. The analytic continuation of zeta, I write it as zeta as well.
Yeah.
Because it's canonical, so I can denote it by the same letter.
Yeah, sure.
Now, this zeta hat is a new function, which is a multiple of zeta by a gamma factor. Okay. All right. And then finally, we have what's usually referred to as the Riemann hypothesis itself, and that's that the zeros of zeta hat of S are on the critical line, on the line real part of S equals 1/2. So this is a hypothesis not proved. The first two parts were proved by Riemann. And I think that once I put in this fudge factor, because I have the fudge factor, then I don't need to say non-trivial zeros. Like the fudge factor also kills the non-trivial zeros. Okay. All right. So, and the reason of great interest in this set of conjectures is because this zeta of S controls zeros of zeta or the hat controls distribution of primes. And this is a question that has interested mathematicians for many, many centuries. How are prime numbers, how many primes there are and how are they distributed? And that's a really complicated question, which turns out to be equivalent to finding zeros, at least at the first level of approximation, to finding zeros of the Riemann zeta function. And you can see, of course, from the Euler product that there is some connection to primes, but what exactly means distribution of primes and how exactly is that controlled by the zeros, maybe we'll talk about next time. Although I have to say that I don't have a good conceptual explanation for that, in the sense that so next time I will explain conceptual explanations for 1 and 2 to some extent. And by conceptual, I mean something that you can maybe explain to someone on a walk in the bush, okay? But third one, of course, is not proven, and also conceptually motivating it is perhaps not as easy. At least I don't know a very good way. But if somebody knows, please write to us on the Slack about your favorite way of explaining the distributions. Oh yeah, the Slack channel is up and running. And one of the first questions I asked was, what is your favorite definition in mathematics? Okay, so I think zeta function is my favorite definition. And I will have another one at the end, maybe, if there's time. But okay, so, and the reason we're interested in this is because the Weil conjectures are the characteristic P analogs of the Riemann hypothesis package. Okay, so Weil conjectures. Which are all proven, are characteristic P analogs of the above package. Okay. Any questions or comments? All right. So
sorry. Sorry,
Yes.
Mr. What did you mean by non-trivial zeros for zeta of S?
Well, right now, there is no mention of non-trivial zero. I'm just saying the only zeros of zeta tilde of S are on real line 1/2. If instead of zeta tilde, you consider zeta, then you obtain some trivial zeros that you have to sort of disregard. And we'll talk about that next time. It's not, it's not so essential for today's purpose.
Okay.
So, right. So before talking about the characteristic P analog, I need to do a generalization. So let's also talk about the generalization. And these are the Dedekind zeta functions. So the first page was about the Riemann zeta function. And now we have the Dedekind zeta function. So what's this thing about? So let K be a number field. What do we mean by that? i.e. a finite extension of Q. So example you should keep in mind is, I don't know, Q, you add square root of 2 to Q, or you add I, or you add, I don't know, some root of a polynomial with integer coefficients. Or with rational coefficient, but you're not allowed to add pi, okay? Because, that's transcendental over Q, the extension will be infinite. By the way, I don't know a good proof of, conceptual proof also of pi being transcendental. I must confess, I don't actually understand pi, but okay, be that as it may, we're not going to work with pi, only algebraic things. So inside here, we have a ring of integer, which, so let OK be the ring of integer. So what do I mean by that? I mean, it sort of almost looks, so, if you're inside Q, then if you're Q itself, then it would be Z. If you're Q adjoint root 2, I think it would be Z adjoint root 2. If you Q adjoint root I, then it would be Z adjoint root I, but it won't always be like that. So for instance, if you're looking at Q adjoint the golden ratio, so, well, Q adjoint, root 5, then I think the integers, like you have to be a bit careful. Maybe it's Z adjoint, I don't know, I don't remember, but it's not, maybe there's some, denominators or something like that. Am I right, Angus?
That's right. That's good.
So up to a finite thing, it almost looks like Q adjoining your, your alpha, but Z adjoining the alpha, but there's a finite discrepancy, which is not so important. So for what I want to say now, so one can show, so this is a ring, and one can show that if we have an ideal in this ring, then if you divide out the size of the ring by, so if you look at OK modulo this ideal, then this is actually finite. Okay. So in fact, yeah, so then we can define the Dedekind zeta function to be the sum over all ideals 1 over norm of I to power S. And when K equals to Q, this just reduces to the usual zeta function, because the norm of, so the ideals in question, so I should say the ideal shouldn't be 0. Any non-zero ideal in Z is are just given by primes, and then the norm would just be that prime P. So sorry, it's given by integers, and the norm is given by that integer. So you get 1 over n to the s. And this also has a product expansion in terms of prime ideals, which are the same as maximal ideals in this case. So that's going to look like 1 minus np to minus s, exactly like the Riemann zeta function. And there is a Riemann hypothesis package for this function as well. So there's analytic continuation, there is functional equation, and there's expected Riemann hypothesis. The functional equation, of course, becomes more intricate and is going to involve what is called the analytic class number formula, which is a really beautiful formula in algebraic number theory, but we don't need to worry about that quite yet.
What is big N of P?
Yeah, maybe I should have written small n. Maybe my big N's and small n's are yeah, it should all be norm. Thank you.
Okay, thank you.
Yes. Other questions? So the following definition will also be useful. Definition: a divisor in K or on K, I don't know, is a finite sum of prime ideals with multiplicity. And then we define the norm of the divisor to be the product of the norms of these prime ideals, I guess, to power ni. And then the zeta function can also be written as the sum over d, if I did things correctly. So here I'm considering non-negative divisors. I don't remember if divisors can have negative coefficients a priori or not. But okay, so 1 over n e to the s. Okay.
And the divisor, it lives in OK, right?
It's a sum of prime ideals. So each prime ideal lives in OK, but it's a formal sum. So I don't mean that you take the sum inside OK. It's a formal sum. Sorry, I didn't.
Thank you.
Formal sum. So I'm not adding ideals inside OK. I'm just taking, thinking of them as formal sum. Other questions?
You were asking about the whether the coefficients can be negative, and I would say in most settings, people would typically allow divisors to have negative coefficients as well, and
Okay.
they might call these effective divisors.
Right. I'd forgotten about that. You see, I'm very rusty in this stuff. If I was a true algebraic geometer or number theorist, I would actually know all this by heart.
Yeah, but we just define it however we want. It's just a matter of
so we
if
can
anyone
define
happens to read another reference, you might notice some discrepancy here and there.
Yeah, so but when I take the sum, I take it over the non-negative one. So that means all the ni's are non-negative. Questions or comments?
So when you say formal sum as well, it should be a finite sum as well?
Yes.
Yeah.
It's linear combination. Okay.
There's a question here.
Can you hear me, Austin?
Yes. Oh, hello there.
Hey, so maybe one useful thing is that, like, if you're thinking about Z, you have prime numbers and prime ideals. And we know that every prime number decomposes into factors. And if you every number decomposes into prime factors with multiplicities. So you can understand prime numbers as just a bunch of multiplicities. So any integer can be thought of as like a function of the primes, as just knowing its multiplicity of each prime factor. But that fails for these rings, but it still works when you work with ideals. So this is like, you take an arbitrary ideal, there is a way to split it into prime ideals with multiplicities, which is akin to what you do with prime numbers in Z. So that's why these like formal sums can be interpreted as ideals, and that relates it to why you're summing over all the ideals. And this product formula is like a unique factorization thing.
Excellent. Thanks a lot, Chris. I actually had that in my notes, but forgot to say it. So yes, this product formula is restatement of unique factorization of ideals in this ring. So there's a great, very interesting history about these developments as well. So this all came about, there was two related things. First of all, it was came about people thinking about Fermat's last theorem. And I don't know if it was Dedekind himself or people around him, they discovered that if it were true that ring of integers in number fields had unique factorization into primes, then they could prove the Fermat's last theorem. But then they discovered that that's actually false. The unique factorization doesn't hold, but the second best thing does hold, namely unique factorization into prime ideals, that holds. Okay, so enormous amount of developments in number theory comes from trying to actually answer Fermat's last theorem on the one hand, and on the other hand, the Riemann's hypothesis. So Dedekind actually, after Riemann's death, so Riemann died when he was 40, and in his wish was that Dedekind be in charge of his, gathering his work, because Riemann had only published 11 papers in his lifetime, which is quite remarkable. And Dedekind spent a decade going through every single note of Riemann and reconstructing as much as he could everything. So I'm sure, although I haven't seen this, I mean, it's pretty natural to think that Dedekind was reading Riemann's note on Riemann zeta function and then thought to also apply it to the more general number fields and came up with the Dedekind zeta function. All right, so as promised, there is going to be some historical interludes in the lecture. So now is time for the historical interlude to introduce some of the main players. So as we mentioned, Weil conjectures are the characteristic P analog of the Riemann hypothesis. So who were the Weils? So I want to talk a little bit about them. So let me see if I so this is a great book that I'm currently reading at home with Simone and with André and Simone Weil. So they were brother and sister, remarkable family. So written by the daughter of André Weil. Simone Weil died when she was 34 years old. The doctor ruled it death by self-starvation. But so now what does Sylvie, the daughter, say about his father? I love this passage, this chapter. Where to find the sugar bowl? My mother endlessly reminds us, you are the daughters of a genius. Often she adds that we are very fortunate. Being a genius, my father obviously cannot remember where to find the sugar bowl, the silverware, or the coffee pot, nor even the words for each object in question. When he needs a knife or sugar, André makes a big hand gesture, a sort of windmill motion. Sometimes he moves his both hands. And where was I? Yeah, 2 windmills. It is up to us, my mother, sister, and myself, to decipher the windmills before running to look for the object. When my sister and I complain, my mother never complains, he explains that since memory is not infinitely expandable, it should not be burdened with useless trivia. I do not know why the sugar bowl's location appears at the top of this list of useless trivia. Anyway, then it continues. So I really love that passage because it's sort of an extreme sort of trait of mathematicians to sort of ignore some normal things in life. But it also emphasizes, I think, something that we should all keep in mind, that there's so much noise in the world. And we have to, especially you're a young person, one of the most important skills is to be able to, filter through the noise. That's to filter it out, all the noise, to really get to the essence. Now, you should be able to say the sugar bowl, but all right. So one day I must be around 10 years old. Since I'm learning to add fractions, André writes for me on a thin strip of paper 1 + 1/2 to the s plus 1/3 to the s, etc. This surprises me. That's it? That's what you're working for? What we're working on? I slide the strip of paper into my arithmetic notebook and keep it there for a long time, like a magic formula. So I like that apt image of the Riemann zeta function, which Andre Weil was working on, was thinking about all of his life. And he wasn't the only one who subject their kids to Riemann zeta function. So this is, so let me see. This is my daughter, who was born exactly 6 years ago today, 8th of March, 2017. And this is she's not very happy putting on a Riemann zeta shirt, which the department bought for me as a gift. She quickly grew out of it to get rid of the zeta function. All right. By the way, happy International Women's Day to everyone. Right. And speaking of women, let's talk a little bit about Simone Weil as well, sister of Andre Weil. Here's a great picture, which I think embodies. So she was. So this is a picture of the Bourbaki seminar, the Bourbaki gatherings. So that's Andre Weil holding a bell on the front. And there is a bunch of distinguished mathematicians, Dieudonné, Ehrlichman, possibly Cartan around. And on the left here, you see Simone, the only person who's actually taking notes. So she was fascinated by mathematics, but very much depressed that she could not be nearly as good as her brother in mathematics, and seriously considered committing suicide as a result when she was 13. And but then after a lot of meditations, she sort of found a use for not understanding mathematics, but still working on it. So you see, she's diligently going to Bourbaki gatherings to write notes and try to understand something. So I just want to read a passage of that. So she turned out to be, we now consider her a sort of a philosopher saint. She was a philosopher that sort of never published a book. She just had some notes that she wrote for herself, and she sort of lived the life of a philosopher like Socrates without writing anything. But after her death, her parents, etc., went through her notes and slowly started publishing her essays. And she has a beautiful essay called The Purpose of Academic Studies, which, since there's a lot of young people here, I would like to read some passages from this essay, which is also on our website. So she has in her writings the sentence, attention is the same thing as prayer. It presupposes faith and love. If we concentrate our attention on trying to solve a problem of geometry, and if at the end of an hour we're no nearer to doing so than at the beginning, we have nevertheless been making progress each minute of that hour in another more mysterious dimension. Without our knowing or feeling it, this apparently barren effort has brought more light into the soul. The result will one day be discovered in prayer. Moreover, it may very likely be felt besides in some department of intelligence in no way connected with mathematics. Perhaps he who made the unsuccessful effort will one day be able to grasp the beauty of a line of Racine more vividly on account of it. So the famous French poet. But it is certain that this effort will bear its fruit in prayer. There is no doubt whatever about it. And then she goes on to say, certainties of this kind are experimental, but if we do not believe in them before experiencing them, if at least we do not behave as though we believe in them, we shall never have the experience which leads to such certainties. There is kind of a contradiction here. Above a given level, this is the case with all useful knowledge concerning spiritual progress. And I should add here, possibly concerning mathematical progress as well. If we do not regulate our conduct by before having proved it, if we do not hold on to it for a long time only by faith, a faith at first stormy and without light, we shall never transform it into certainty. Faith is the indispensable condition. So it's an interesting philosophical question, I think. Also with regards to math, you have to have faith in what you're trying to prove to actually try to prove it. So I think there's two kinds of mathematicians. Some of them, when they see something they want to prove, the first thing they think about is try to figure out counterexamples, right? I think Angus was telling me that he belongs to that category. Whereas me, I'm in the naive category of like believing everything that everybody tells me and wishing it to be true. You know, so I'm in the category who has faith to start with and then tries to prove based on faith. Anyway, this is a beautiful essay of Simone Weil, which you can read on the website. And there's many other very interesting writings of her. And she's far more, by the way, famous than her brother. I don't think I put in a passage about that, but she, for instance, when the daughter of André Weil, she got the first prize in the French concours, which is the, you know, all the French high school students have to write one exam, all of them, to get into university. So, you know, tens of thousands of people write this exam, and she became first. And as such, she met the president of France at that time, who was no other than Charles de Gaulle, who was the French resistant hero. And she has this beautiful story in the book that when she met with de Gaulle in front of all the cameras and huge numbers of people, the only thing that de Gaulle told her was, "I admired your aunt a lot." It's so no mention of her or her father, who obviously don't count, but only of her aunt. So Simone Weil is far more known in wider circles than André Weil. But okay, so what I want to talk about, where this story is taking us, is the letter, a letter that André Weil wrote to Simone Weil explaining his mathematical universe. So, and this is part of the letter that I put here. It is widely believed that there is nothing more to do about algebraic functions of one variable because Riemann, who discovered just about all that we know about them, excepting the work of uniformization by Poincaré and Klein, etc., left us no indication that there might be major problems that concern them. I'm surely one of the most knowledgeable persons about this. André was not known to be humble, mainly because I had the good fortune to learn it directly from Riemann's memoir, which is one of the greatest pieces of mathematics that has ever been written. There is not a single word in it that is not of consequence. The story is not closed, however, he goes on to say. And then he says, my work consists in deciphering a trilingual text. See, for instance, the Rosetta Stone. Of each of the three columns, I have only disparate fragments. I have some ideas about each of these three languages, but I know as well there are great differences in meaning from one column to another, for which nothing has prepared me in advance. So what I want to talk about now is this Rosetta Stone of mathematics that André Weil talks about in this letter to his sister, which is a dictionary which helps him navigate, for instance, between characteristic 0 and characteristic P. Okay. Before going there, let's have a picture of the Rosetta Stone. So this is the Rosetta Stone on display in the British Museum, the most visited object in the viewed object in the British Museum. So this is a decree by one of the kings of Egypt around 200 BC. And the key about this is that it's essentially the same decree in three different languages. The hieroglyphic language on the top, the Egyptian demotic on the middle, and the ancient Greek in the bottom. And so people were fascinated with the hieroglyphs. So, you know, these are when the letters actually look like actual objects. And they wanted to decipher what this means, and they had no idea for many, many centuries, because of course everybody was fascinated by the Egyptians and the mummies, etc., but they had no idea what they were finding in the caves. And this discovery of this stone led to the decoding of the hieroglyphs, because of course people knew ancient Greek, and so therefore they could reconstruct what things meant. Now, the mathematical Rosetta Stone is a bit different because all three columns are mysterious, so to speak. But nonetheless, they all talk to each other, and by thinking about and meditating on these three different columns, one can sort of understand a lot better each of these columns. So let's move on now. So the historical interlude, we go to the back to mathematics. And so what is the Rosetta Stone of mathematics that Andre Weil talks about to his sister? So this has 3 columns. On the one column, we have number fields. In the other columns, we have algebraic curves over positive characteristic, or if you wish, sometimes this is also, you can think of it dually as function fields. And on the third columns, we have the Riemann surfaces. So if you think about a number field K, then you should think that in our dictionary, K corresponds to rational functions on a algebraic curve or functions on a Riemann surface. And if you look at the ring of integers, then instead of rational functions, you will be looking at algebraic functions or holomorphic functions. So here we're using another great discovery of Riemann, that Riemann surfaces are actually algebraic. So this comes down to existence of enough meromorphic functions on a Riemann surface. So and then if you are interested in prime ideals inside OK, so remember, these are the objects of great interest for us because this is how we build our zeta function, right? Using prime ideals or divisors. Then you should think the analog of these are exactly the points on our curve. On our curve X over the finite field, or equivalently, well, over complex numbers, the analog should be points of our over C. And then what Riemann, what Weil worked on for most of his life was, okay, his idea was, let's take the deepest thing that we could dream of about number fields, which is the Riemann hypothesis, and let's see if we can translate it to the function fields or to the algebraic curve world. And he came up with the Weil conjectures through this translation. Okay, so we will discuss this more, of course. So that's what in some sense, the whole course is about how this translation happens and what one can say about it. And then if you go over C, then perhaps all of this for curves anyway reduces to Riemann rock. It's so I will talk more about this. I don't know if they had a very good analog over C, but possibly the Riemann rock, which is one of those formulas that is extremely important that I've never actually internalized in a way that I would like, in a way that I can sort of explain on a walk around campus. So, and then Weil noted, first of all, Weil proved those conjectures for curves, but then he noticed that actually these conjectures, there's no reason to stop at curves. You can formulate them for higher dimensional spaces. So they became known as the Weil conjectures that sort of created a lot of excitement in the mathematical community in the 1950s and 60s and 70s. Okay, so now what I want to do is explain how we can go from Riemann hypothesis to Weil conjectures for curves. Any questions?
We have a chat question.
Oh,
Yeah. Asking if Weil had a permanent position.
Oh, well, that's a great question. Andre Weil, he has a great history. I mean, we'll get more into it, of course, during the lecture series, but he had a position in France, but then the Nazis came, and he was at the time actually in Sweden when the World War broke down, somewhere in Scandinavia, maybe Finland. And first he was arrested on suspicious of being a Russian spy, and you know, they were going to execute him. And then I don't know, some mathematician or somebody intervened, so they didn't execute him, and they extradited him to France. And then in France, he was imprisoned because he refused to join military service, because he said that my work in mathematics is much more important than anything that I could do on the battlefield. So they threw him in prison. And then in prison, he threatened to commit suicide unless they allow him to have pen and pencil and his mathematical books. So eventually he got those. And so anyway, so then he was, you know, a refugee of war. Eventually, his relatives got him out, went to the US, went to Brazil for a little while. He was in the US teaching at Lehigh University, actually, but he was not really appreciated there, and then went to Brazil for a little while. Eventually, he went to University of Chicago. He was a professor there for 10 years, and then at the Institute for Advanced Studies for 30 years after. So yeah, lots of interesting history there as well. He was the only member of Bourbaki who was away from France. Yeah, I don't know if he was the only one, but yeah. He was one of the founding members of Bourbaki. Okay. Other questions or comments? All right. Okay, so now we have to discuss what is a point. What is a point on an algebraic curve? Well, first of all, what is an algebraic curve? Well, okay, just as a first approximation, consider the plane curve, you know, y squared equals x cubed plus x squared. That's a perfectly good curve. It's an, well, it's 1 point less than what's usually called an elliptic curve. Okay, the elliptic curve is completion of these. And polynomial functions on this curve on x are of this form. Okay. Now, we want to understand what a point on this means in terms of this ring. So here's the key question. Can we see the points?
You write down the
Yeah. Do you mean x, not x squared, right?
Sorry?
Do you mean x squared, x cubed plus x?
Oh, well, okay, sorry. It doesn't matter.
Or would it still be algebraic?
Oh, the algebraic just means it's given by polynomial. So yes, it will be algebraic.
It wouldn't be smooth though.
It wouldn't be smooth, but I don't care. Yes, sometimes we will care, soon we will care, but right now I don't think we need to care. Thank you. Yes, good point. Other questions or comments? You see, point is somehow a topological concept. So if we want to do things algebraically, we have to translate everything from topology into algebraic terms. So can we translate the concept of point into a in algebraic terms? So in terms of this ring, and in algebraic terms, I mean in terms of the ring of functions. Okay. Now, there is a general philosophy that I remember, actually, I learned this when I was in undergrad. I was working with as a summer research student with a professor who was working on C-star algebras. And I was helping him write a book on C-star algebras. And then I came across, while in the library going through some books on C-star algebras, I came across this general principle, which sort of blew me away at the time, though I couldn't quite understand why. So here's a general philosophy. So the general philosophy is that space, if you want to know information about space X, So so this is another dictionary that we're going to employ. So on the one hand, we have, topology or geometry on the one side, and on the other hand, we have algebra. And okay, if you have a space X, then in the algebra side, we have the ring of functions on X. So functions from X to whatever you want, like C or R, let's say C. And then the key, so, okay, another part of this philosophy is that points of X should correspond to maximal or prime ideals, depending on your taste, in this ring. How? So if you have a point in here, you should send it to the maximal ideal consisting of all functions that vanish at that point. Okay. Now, this is the general philosophy, but there are instances that one can make this precise. So for instance, there is something that's called Gelfand duality. And this is what I read in the context of C-star algebras. So which says that, so there's a precise equivalence of category. Of course, Gelfand didn't phrase it this way. Within compact topological spaces, equivalence of categories with commutative C-star algebras. Is once, no, I guess C-star is not it's without the bold C, right? Okay, C-star algebras. Exactly by this map that we said before, this is an equivalence where if you're given the set of maximal ideals inside the C-star algebra, you endow it with what's called the Stone Gelfand topology, and that's what allows you to recover a topological space from a commutative C-star algebra. And I've already explained how to go from a compact topological space to a commutative C-star algebra, namely, you take functions on it. Okay. So I remember being totally blown away by this when I first saw it. And now that I look back to it, it's because it's sort of, this is like essentially the starting point of modern algebraic geometry. Somehow for me, this is telling me that I can understand points and, from the ring of functions, not just points, but sometimes even topology from the ring of functions. Okay. So, any questions about this? There's also this great book by Milner, by the way, Topology from Differentiable Point of View, where he also talks about this philosophy. So in the first chapter of it, he talks about how functions on a topological manifold or on a differentiable manifold determine that manifold and how to work with that. Topology from Differential Point of View. Really fantastic book. Okay. Any questions about that? Comments? Have you guys seen this principle before?
Oh, sorry. Can you hear me, Mr.?
Yes.
Okay, good. What happens in the non-compact case? Does it just fail?
No, I mean, of course, I think it's still true once you add in the correct adjectives, but I'm not the expert, right? It's you add in enough adjectives, you have to add in some adjectives, right? It's but I think, yeah, I mean, if you look, for instance, in Milner, he doesn't consider compact manifolds. He considers general differentiable manifolds. And basically he says that many things that you want to know from manifolds, you can learn from his ring of functions. Now, of course, if you're a geometer, you would be weirded out by this because you're like, why do I give up on geometry to work with this with ring, which I have no intuition with. When you're working with geometry, you can draw things and you can visualize them. But the point is that when we want to work over characteristic P, then we lose all of that intuition, right? So we have to, the only thing we have in characteristic P is this ring of functions in some sense to start with. And then we rebuild all of that intuition from this ring of function. That's somehow how things go. Other questions or comments? Thanks, James, for the question.
So one thing which I absolutely love about this is that this like philosophy sort of isn't it's not just like some idle thing. Like it's actually really, really, really useful to just even like understanding commutative algebra. Once you know this sort of translation, lots of things in commutative algebra become like obvious or natural. And without it, they become like, why would anybody ever do any of this? So like, I find this a very, very, very useful thing to think about on a practical level. Like, how do you organize a subject in your head when geometrically you can just like see it? It's very, very
yeah,
useful.
it's absolutely true. And for me, algebra without this geometric intuition I just cannot keep it in my head. Like, for instance, we had a talk on Monday in our university by an expert in Hopf algebra. And I was really struggling because I just wanted to translate everything into geometry, but there it wasn't possible because, they're considering sort of non-commutative algebras. And so here, okay, I should emphasize this is commutative algebra. And the story of non-commutative geometry is more complicated. So I couldn't translate things into geometric terms, and therefore I couldn't understand what's going on. The only way I can understand algebra is if there's some geometry to guide me. Different people are, of course, different. So yes, absolutely. And this philosophy and that, and also the Rosetta Stone that I mentioned, these are living things. Like, people are sort of working on this all the time. So for instance, another example of the Rosetta Stone was when Drinfeld translated the Langland's conjectures from the number field case into the function field case and actually proved the GL2, for which he got a Fields Medal. So he was meditating on the Rosetta Stone for a long time to sort of figure that out. So these are, and it's very much continuing up to the present. Okay. Any other questions and comments? All right. So, right. So how should we think about points? So let us define the points of a curve X to be the set of maximal or prime ideals. Again, I won't be so specific right now. Let's say over any field now on the ring of functions on X. So let's do an easy example. Just a line. What are the points on a line? Okay. So what is a line? Is just, I denote it by A1. This is a weird thing we do in algebraic geometry. We denote, so this is, the ring of functions on this is spec. Sorry, not spec. The ring of functions is just Kx. Just a polynomial algebra. Okay. So what are the points in here? Points on A1 are given by prime ideals in here. So irreducible polynomials. Okay. So I'm interested in the case of K equals to FQ. So the line then on FQ, so we have, so then A1 has Q points. So namely 0, 1, 2, ... Well, okay, sorry. The points identify with the vector space FQ itself. Because the irreducible polynomials are of the form x minus alpha, where alpha is in, oh, sorry, no, that was wrong. So these are the FQ points. I'm saying nonsense, sorry. Of course, I can have, if it was algebraic closed, okay. So let me keep that because it's useful. If I was over an algebraically closed field, so let's say FQ bar, then this, then irreducible polynomials are of the form x minus alpha, where alpha is in FQ bar, right? Because all polynomials factor into linear ones, and then you get one irreducible polynomial for each. So let's say if you're over C, then the points of the line are just in bijection with elements of C, which is what we hope is true, that the complex line is just what we think the complex line should be. Okay? But if we're working over a field which is not algebraically closed, then of course, irreducible polynomials need not be linear, right? So over FQ, irreducible polynomials need not be linear. So we define, so moreover, when you take the quotient, by the way, if you're not familiar with FQ, you can replace everywhere here Q by P, a prime. So then you know what is a finite field with P elements. Okay, and then if you take the quotient, this is always going to be by a maximal ideal. So this is always going to be a of the form a finite extension where n is the degree of that polynomial. So the only prime ideal that I throw away is the 0. Okay, and now let's define. So points are for me. So points are by definition irreducible polynomials of FQX. And I define the norm of a point, you see, because I want to build that dictionary, right? Now I have my point, and I'm now going to define the norm of that point to be the size of the quotient. So it's the size of this quotient. Which is Q to some power of the degree, okay? And now I can define my zeta function, namely the zeta function associated to X. So this was, okay, so this was an example. I gave it as an example on the curve A1, but actually this procedure works on any curve. You just have to be a bit careful. If your curve is not a plane curve, then you have to look at functions locally. Okay, so there's a bit of a dance involved, but you can always, points are essentially, you should think, are maximal ideals, and we can define their norms in this way. And now we can define the zeta function of the curve X.
Sorry, can I say this?
Yes.
Is P here just the ideal generated by F?
Yes, you can think of it that way.
Okay, it's just the left-hand side of this, the last line has n of P, and the right-hand side doesn't seem to have P in it.
Yeah, my notation wasn't very good, so thank you very much. So, so let me make this clarify. Thank you. Sorry, points are by definition irreducible polynomials, and a point P, I'm denoting the irreducible polynomial corresponding to a point P by F, And then I'm defining NP to be the order of the residue field of that irreducible polynomial. Does that make sense? So yes, P equals F if you want. It's just that we want to slowly disassociate ourselves from always thinking about irreducible polynomials. We want to slowly actually think of these as real points. Okay, so now that we know how to define them, we want to bring the intuitions of actual points as you think of them in topology into the play as well. So that's why I don't want to denote them by F, which is an irreducible polynomial, because I really want to think of them as points, which are a point for me is P, and F is a irreducible polynomial. And even though I've defined them to be the same, I prefer to keep the separate notations. Is that okay? Does that resolve the confusion? Sorry, I see some questions on the chat as well. Okay, so let me go to the next page to define the zeta function. So definition of zeta function of x when x is a curve. And this is due to Artin, actually. Artin was the first person that wrote down this definition. So what did he write? So the definition is very much just, you basically copy the definition from the other part of the Rosetta Stone. So it's a sum over, let me write this down, d bigger than or equal to 0, 1 over n ds, where here d is by definition finite sum of points. Okay, and ND is, again, by definition, is the product of the NPs. To the power NI. So literally I'm copying things, right? That's, so this is, I mean, so this is the beauty of this part of Rosetta Stone, is that once you set things up, you can basically, the same definition works in the two columns. You know, it's like once you have the right notions in place, you don't need to think. You just write down somehow the exact same expression and it's the right object. Okay. And furthermore, we have a Euler product expansion for this sum. Okay. And that again comes from the fact that, you know, these NP is multiplying correctly. So that's the definition. We're taking, so let's just remind what we're doing. We're taking a bunch of, so what is this D? D is the sum of finally many points. In other words, finally many irreducible polynomials. And ND is the size of the residue fields of these irreducible polynomials when you mod out the ring of functions module these irreducible polynomials, okay? Very simple things, as it should be, because it should mimic primes in integers, right? So this should be something simple. Let's do an example of the affine line. So this is for general curve example. X equals to the affine line. Now, what is D? Who can tell me what D is? So remember, P, so the set, sorry. So P is the set of points. So P equals, my notation, maybe I should denote it by curly P. So curly P here is the set of points, which remember is the set of irreducible polynomials on FQ or in FQX in this ring of polynomial ring. And what is D? Well, D is a finite sum of these things, right? But the saying finite sum is a bit misleading. Actually, better to think of it as product. Okay, so this is the set of all, actually the set of all polynomials of degree bigger than or equal to 0, because you multiply the irreducible polynomials, that's what you get. So, I mean, maybe what threw people off is that I've written here this D in additive notation, but of course I could write it also in multiplicative notation, you know, then it would be closer to multiplying polynomials. Okay. This is crucial, okay? Any questions about this?
Also, just the polynomial should be monic, I guess.
Oh, right. Because two different, because rescaling gives you the same point, right? Thank you. Monic. Because what really matters is the ideal, right? And so, yes, thank you very much. So it's great that we have actually some algebraic geometers in the audience who can correct me when I.
Masood, I think you've also got an extra inverse in your Euler product.
Oh, right. Yes, sorry. Sometimes I put the inverse, you know, yeah, thanks. Any other mistakes or comments, questions?
Oh, maybe a comment just worth thinking about in this context is that, like, in integers, you can't put your primes into a bunch of nice boxes. Like, there's no natural way to partition the primes into boxes. But in this world with a polynomial ring, you have the degree function. So all of a sudden, your primes have like a measurement of how big they are. And that's what lets you break up this sum really nicely. You know, measure the size of a prime or the size of a product of primes by the degree.
But wouldn't you say that the degree of a prime in integer is just P itself? I mean, it's the size of Z mod P, right? Which is P.
But that's not additive. So like you, because that's why you need log P if you want to start giving size of primes in the integers. Right, like the at least for this thing, if you take two primes and multiply them, their degrees add, which is what you want. And you can't do that with integers unless you introduce log P's everywhere, and then it's no longer like in nice boxes. Okay. Actually, that's something that I would like to think about more, because it might explain, you know, why we see logs everywhere, right? So, yes. So let's continue that thought. Thank you very much. A little bit later, I think that there's something there that, but we will also discuss at the end in 10 minutes or so why this setup is better than integers, at least a priori. Okay, so now let's compute our zeta function, right? So let's just compute. We can, in this case, explicitly compute the zeta function, pretty much the only case you can do this. Well, not the only case, but the only case we can do today. So
Masood, can I ask a quick question? So the D, you had additive notation for your finite sums, and then if you look at your zeta function, it's not really about D, it's about the norm of D. So that's just telling you what combinations to sum over, right?
Yes.
But what I don't quite get is why, okay, so it's clear now that there's the multiplication instead, but you say D is the set of all monic polynomials. And that's because, I mean, is that exactly every polynomial you want there is uniquely determined by some set of primes, prime ideal?
That's unique factorization in the polynomial ring.
Ah, I see. Okay, that makes sense.
Great.
Thank you.
Thank you. Excellent. Very good question. All right. So we have to do this sum. Let's just do it. So how many degree D polynomials do we have? Well, it's monic, right? But then you have D coefficients, and it could be whatever you want, right? So there's Q to the D polynomials of degree D. So this is number of monic polynomials of degree d. And then I have to multiply by 1 over n. And then what is the size of the quotient field? Well, that's the degree of the polynomial. So that's q to the d, and then I have to do to minus s. Okay. And that's the norm. Norm to the power minus s. So this is the contribution of the norm, and that's the contribution of the how many polynomials we have. Okay, so this is a simple geometric sum. So we get 1 over 1 minus q to 1 minus s. Just a geometric sum. So that is the zeta function of
Masood,
yes.
do we want the power of s in the denominator to be positive or negative? Because I think it was positive earlier.
Yeah, I keep messing up positive and negative, don't I? Which one do we want to get that answer? So I think the final answer is right. This thing.
Yeah, the one in the sum needs to be changed.
So this one should be
1 on q to the ds.
okay.
And similarly,
Oh,
one
and
on
also
n to
this
the d
one,
to
right?
the
I
s
wrote the
and yeah, there you go.
sorry. Yeah. Up to sign, everything will be true, right? It's a okay. Now, now there's something amazing that happens in the geometric, in this world over finite field, whose analog we do not know over integers. And that's that we can complete curves to become a compact object. We can compactify. So remember, we can compactify R, and its completion is, so like 1-point compactification becomes the circle. Okay. Similarly, we can compactify A1, and so that's just going to be A1 adjoint 1 point at infinity. And more generally, we can canonically compactify every smooth curve to a projective curve. Or in other words, we can compactify any Riemann surface into a compact Riemann surface in a canonical way. And this completion is what's going to give us the fudge factor in this world. Okay, remember I told you the Riemann zeta function, there's this fudge factor with the gamma function that's mysterious. Well, the completion of the zeta function in the world of algebraic geometry is completely unmysterious. You just complete your curve in a canonical way. So, and then once you compute the zeta function of this completed curve, so this is a very key idea of existence of canonical compactification. Okay, there is no way, we do not know of a way to compactify integers. Okay, we don't know what that point at infinity should be. That's somehow one of the key difficulties when we're dealing with number theory. But when we come one step in our dictionary, situation becomes much, much better. So we know how to compactify. So let me write this as an exercise for you. Compute the zeta function of, so show that the zeta function of P1 is equal to 1 over, well, this is the A1 part, and then you're going to have the contribution coming from the infinity. That's going to look like this. Okay. So this is the this is what we already computed, the A1, and this is going to be the point at infinity. That's going to be the contribution of it. And that's the right fudge factor. And observe that this is a rational function in t equals q to the s. So it's going to look like, in other words, in the variable t, it looks like 1 over 1 minus q times, maybe I should put minus s, qt times 1 over 1 minus t. Okay, so q is some number like 5 or 7 or 35, like not 35, it has to be power of prime. Okay, like 25. Okay, so this is a rational function. It has 2 poles and no zeros. Okay, so not a terribly interesting rational function. But the situation becomes much more interesting when you consider the case of general curve. So, and here is the Riemann package. So I want to end by talking about the Riemann package for smooth projective curves. Okay. So by the way, when I make this change of variable, I denoted the new zeta function by zt. Okay. So generally, I denote, so now let x be an arbitrary curve. So x smooth projective over fq, and I define zx of t to be, it's just a convenient way of writing well, this is the zeta
Before we
function.
go on, can I ask a quick question?
Yes.
So you said that you obtained a fudge factor by completing the curve, but you also said that over z we don't know what completion is. But for me, the fudge factor, it appears precisely when we work over z or q in the initial setting of the beginning of the talk. So I'm a bit confused. Well,
I'm saying that we don't have a good geometric understanding of the fudge factor over z. That's
I see.
Here, the geometric meaning of the fudge factor is completely clear. It's completion. But over z is completely mysterious. Somehow, the geometric meaning of it is mysterious.
Great, thank you.
Okay, so let's write the Riemann package. So one is that z of t, zx of t is a rational function in t. In t of the form p of t divided by 1 minus t times 1 minus qt. So the denominator is exactly like p1, but then you have a numerator where the numerator is a polynomial of degree 2g, where g is the genus of our curve, or equivalently genus of the corresponding Riemann surface. Okay. Part 2 is the functional equation. I write it in terms of zeta now. Zeta x of 1 minus s is q to 1 minus g times 1 minus 2s times zx s. So there's some, it's almost zeta x 1 minus s equals s, but there's a factor of q to some power. Okay. And the third, which is the Riemann hypothesis, is p of t equal to well, let's write it as a product of linear things. So these are the roots of p of t. So these are the zeros of the zeta function, and the claim is that the absolute value is q to the minus 1/2. So in other words, in terms of our variable t, this is saying that the real part of t is 1/2. Remember that t is q to the minus, wait. Yeah, maybe I won't say that. Let's leave it like that. So once you take the once you take the log, so minus the log is 1/2. That's, did I get that right? Hold on a second. I think so. Or maybe it should be plus 1/2. Again, my plus and minuses are a bit. So this is the analog of Riemann hypothesis. So Andre Weil arrived at this. Well, first of all, this was proved by Artin for elliptic curves. So curves of genus 1. And then Andre Weil, to prove this, actually Andre Weil had to rewrite the entire foundations of algebraic geometry because he had to introduce the notion of Jacobian, which for curves over positive characteristic. And by the way, he made the announcement of the proof of this in 1940, exactly when he was in jail. So he wasn't sure if he's going to survive. He just wrote a 4-page note. He's like, okay, I think if you do this, you're going to prove the Weil conjectures for curves. And then maybe, I don't know, many years later, actually, his paper came out once he survived the war and jail, etc. So now, what I will explain next time is that, so this is for curves, and of course, we're going to talk about a version of this for higher dimensional objects. So for curves, it was proved by Weil, and then the higher dimensional case was conjectured by Weil and proved by other people. But just as the zeta function captures or controls the distribution of primes, here the zeta function of the of curves controls the distribution of the number of points of curves over finite fields. So we will talk more about that as well. I mean, why that's the case next time as well. Okay, so there's two things we're going to discuss next time is points of the curves over finite fields. So what does that mean? That means essentially you're trying to find solutions to polynomial equations over finite field. Okay, so let me summarize the lecture. So think about a Riemann surface. Okay, so so Riemann tells us that, you know, this object is algebraic. So in other words, the change of charts are given by some polynomials. Okay, and now we consider these polynomials. Essentially, let's think of them, you know, they're defined over some ring of integers of some number field. Okay, let's say that's the case. Then we can reduce modulo powers of prime to count how many solutions these polynomials have, modulo primes. And the Weil conjectures for curves tells you sort of what the distribution of these points look like. And it's exactly this Riemann hypothesis that will tell us that. So, and moreover, what it tells us is that you can also see some parts of the topology of curves this way. So, for instance, you see the genus appearing. So we can read the genus from the zeta function, and the Euler characteristic, etc. Okay, I think this is now a good time to end. So thank you everyone for your attention, and yeah, happy to answer any questions or comments.
Thanks, Masud. I enjoyed that, especially the stuff about Weil.